presentation will be on Zoom, and is from ARASH AMINI BARDPAREH. He was an electronic engineer, graduated at the Kashan University in Iran. He then pursued his master degree in electronic embedded system at the Politecnico di Torino in Italy, where he's currently doing his PhD at the Department of Control and Computer Engineering, where his primary focus is on hardware design on FPGA. And the topic of today will be similar to the first one. We will share his experience from his master thesis about the implementation of TDC on FPGA for charge particle therapy in cancer treatment. Arash, you can share your screen if you like.
Hello, can you hear me?
Yes, we can hear you. I think it's... we're not sharing.
Yes, I'm trying, but I have some errors. Okay.
Because it's the room sharing. Okay, now let's, so we will share the slides, and please tell us when to move from one slide to the other.
Now there's a problem, okay. Just the system is crashed, the Zoom is crashed.
Do you see the slides?
I see the slides, but I have a problem loading the screen. Maybe I should disconnect it and reconnect, I don't know.
So if you see the slides on our Zoom, you can just tell us when to move. Is it still there?
It's suspiciously very, very still.
Are you still there, Arash? Andiamo alla prossima presentazione.
Vediamo se l'altro speaker è pronto.
Tutto sarà qua.
Ok. Magari mo se si riconnette, diamogli un minuto. We will wait 1 minute if you reconnect, otherwise please the next speaker.
Okay, so let's wait 1 minute. Okay, Arash? Can you see the slides?
Yes, sorry, I don't know what happened.
Okay,
yes, I can see this.
Please start and tell me when to
Okay.
change slides.
Okay. So I should share my video, but it's impossible now. I don't know what is happening. Okay, can you hear me very well?
Yes, we hear you.
Okay. Hello everyone, I'm Arash. I'm here on behalf on our team to share our experience and observation during implementation of time to digital converter in Xilinx FPGAs especially for specifically for charge particle therapy. Can you go to the next slide? Okay, first I will introduce the project Hybrid Online Technology for Particle Therapy, which is a PRIM project founded by Italian Ministry of University and Research. And it is a collaboration between Politecnico di Torino, University of Turin, and the INFN. If you can go to the next slide. The basic idea is having a data acquisition system for charged particle therapy. Charged particle therapy is a advanced method of cancer treatment using charged particles, typically protons and carbon ions, to focus to target the tumor accurately. And the idea is the particle passing through a sensor, hitting the target, losing some energy during the treatment, and do some reflection. And also the reflection is captured by other sensors. monitoring these beams is very important to know the efficiency of the treatment. So one of these characteristics that we have to measure is the time difference and time of flight of these beams during the treatment. So if you can go to the next slide. So for this case, we need time to digital converters. Basically, time to digital converters are electronic devices to measure time with a very high resolution. And there are available ASIC modules like Pico TDC from CERN or TDC from Caen, but our aim is to integrate these TDC with the FPGA-based data acquisition system. If we can go to the next slide. The most famous architecture among all available ones to implement the time-to-digital converter on FPGA is tap delay line, which is basically propagating a signal through a series of delay elements and capture the state of the line at the time that the second signal arrives. It is very famous because of the simplicity, and it also provides a very good resolution. So if we can go to the next slide. Okay, when we want to implement the TDC on FPGA, we have limited resources that we can use: the lookup table, multiplexers, and registers and carry blocks, which also you can go to the next slide. Which we use carry logics, and they are always used because they are fast and they can easily be cascaded, and also they. Can you go to the next slide? Because I don't have that. Yes, and they also have a very short route to the available registers. Okay, you can go to the next slide. After implementation of the delay line on FPGA, here you can see a view of how the carry logics are cascaded in on the device, and also you can see the simulation, the timing simulation after implementation doesn't show the delay inside the carry logics, but just the total amount of delay after each carry logic. And so the simulation doesn't provide us a very good and accurate view of how this delay line will work, and so because of that, we have to move on. We had to move on to the experimental test to see how it works. You can skip the next two slides because yeah. Okay, what we expect on the experiment was as the signal propagates more, as the delay we want to measure is more, these registers becomes high linearly, and the delay can be simply measured by knowing and finding out how much is the delay, and just by counting these outputs, which is also known as thermometric code, to the delay. You can go to the next slide. Thank you. But in the reality, there are bubbles in the middle, and they can be due to different routes, different routings, and also due to variation in fabric, because the FPGAs are not supposed to be used in a sequential circuit, combination of circuits, and with these picoseconds of accuracy. So there are two ways you can see. You can just take the last high and don't care about the bubbles, but you will lose lots of resolution. But you can also count like it is also known as reordering. Count the number of ones and try to calibrate the TDC by finding out the beam width of each of these delay elements, and get the output. Okay, so if you can go to the next slide. Okay, One important thing is also it is mentioned in previous presentation is that the delay lines should be kept in one clock region to avoid the clock skew. What we experience, the maximum amount of delay lines that the delay elements that we can implement to be in one clock region, specifically in the board that we use, Kintex UltraScale KCU105, was 464 tabs, which is generated by 58 carry 8 blocks. And the maximum range that we could measure by this line was 2.8 nanoseconds, which is not enough. And because of that, we have to integrate delay lines with the synchronous count. We can go to the next slide. The basic principle is having delay lines to measure the time difference between the arrival of the signal and the next rising edge of the clock. And the counter counts synchronously the time passed in the large amount of time that passed in the middle. And eventually the time can be calculated simply by following this formula. We can go to the next slide. The final back diagram of what we implemented on FPGA is having a delay line for each channel and a synchronous counter, and do the calculations through DSPs and save the data into the memory, into the VRAMs as a histogram. The bit counters was somehow a bottleneck because they are very slow, also due to the bubbles in the middle. So they are the basic idea was grouping the outputs of the delay lines and count the number of ones parallelly. And our aim was matching our measurement rate in the treatment. We can go to next slides, maybe pass also the next, because I explained them. Also the next one. Yes. Also, I have to mention that the sensor that the FPGA interconnects with the FPGA is Abacus. It is a 15 micrometer thin SiC gain avalanche diode sensor segmented into 146 strips. It has 624 channels, each having charge sensitive amplifier followed by a leading edge discriminator. The output of the Abacus the Abacus gives us 2 nanoseconds with signals, and the average clinical rate that we want to measure that we want our TDC to comply with is 1 megahertz. So we designed the TDC to work up to 10 megahertz of measurement rate, and due to this. Okay, I forgot to mention something, but it's already mentioned in the previous presentation. The clock period that the counter counts should match the delay line. So the delay line, which I said it can measure up to 2.8 nanoseconds. So it gives a limit to the period that the counter will work with. So we chose 400 megahertz, and with 400 megahertz, we might lose signals because they have a short width, 2 nanoseconds, and for this we had to use some latches, combination of some logics to keep the data and not losing any measurements. And okay, we can go to the next slide. There is a very specific thing that I never seen in mentioned a lot is when you want to implement a TDC, when I wanted to implement a TDC, there are lots of errors. For example, there are routes from the IO pads to the delay lines, also including the logics that I use to capture the signal. And if there is any asymmetry in these paths, and so if you set constraint to cascade the delay lines, but leave them alone to be placed automatically by Vivado, we might have some errors. For example, if we have the exactly 2 signals in the same time at the input input ports, If the path between them and the delay lines are the same, we might have the same signals enter to our delay lines. But if these paths are different, we might have some extra offset. Also, if the path from delay line to delay line 1, which is our first channel, is longer than the second channel, we might lose some data because the TDC is designed to capture the first signal, start counting, start measuring, and then stop counting when the second signal arrives. But if we have this negative offset, we might lose some data. And we can go to the next slide. Okay, and another thing is when you are trying to combine delay lines with a combinational, which they are not working properly in a proper way with the clock, but with the synchronous clock, you are mixing two types of design. I had this experience during my measurements that when I wanted to, as this graph shows, for example, when I wanted to measure like 600 picoseconds with a TDC not well calibrated in the terms of the delay lines, I had also some measurements, one clock cycle more and one clock cycle less. And this could happen because the counter enables it is synchronous, but it enables counting when the first signal arrives and disables counting when the second signal arrives. So what will happen if these signals happen very close to the rising edge of the clock and the counter not exactly sense these signals as the delay line sense them? It could start counting one clock cycle after, or it can happen in the opposite way. So the counter and everything, the delay lines counter any any registers that we use, we try to implement them multiple times to find and remove these offsets and these errors. And we manage to remove these errors, but what we are trying to do is finding a methodology to facilitate this design for each channel that we want to add. We can go to the next slide. And here's the final implementation on the device. At the end, what I designed was each delay lines in different clock regions, but in the same column, to have specifically the same routes from internal ports to the delay lines to the each register, each latch or register or any logic that I use to capture the signal, and from that to the entrance of the delay lines and also matching the counter. We can go to the next slide. And here is the result of measurements of TDC with the TDC, not very well calibrated, but just to test the whole setup altogether. The calibration was not completely with the code density test, but we tried to run many tests and find the bin width from every bin, and it works. But the maximum, the errors from the counter, as I mentioned, and also external offsets are removed. But the maximum error from the median of the measurement for us in these measurements was 25 picoseconds. But the problem was the standard deviation varies a lot, and the output of the TDC was not following the Gaussian distribution. Also, the left picture is the whole measurements from very short, from I don't remember, from like a few hundreds of picoseconds to 4 nanoseconds, and here is the input output of the TDC. And the right picture is specifically when we measure the 2,200 picoseconds, which was one of our best outputs, which as it shows was not very good. And we can go to the next slide. So what we came up, instead of doing the code density test, we had an idea to implement a machine learning approach with a multiple layer perceptron with 64 neurons. We give the output we remove the encoder and the bit counter and completely give the results of the measurements of the delay line 1, delay line 2, and the counter to this model, and try to train it. And we can go to the next slide. And as you can see, here in the left is one of our worst measurements when we were measuring 900 picoseconds, and the results was very bad. But after implementation of this, after using this machine learning approach, everything looks very much better, and the standard deviation reduces a lot. Also, I put same measurement result with Pico DDC from CERT. And also in the next slide, you can see the distribution of the error, which is much less than before. We can go to the next slide. To finish this presentation, calibration with the neural network seems very good, but there are some problems, which is now it is like offline. So we measure and then we try to get the outputs with the machine learning. But what is our aim is to integrating the systolical accelerator into the TDC inside the FPGA, but the speed is somehow up to now is like a problematic for us, which not match our clinical rate of measurements. And also as a next step, we try to, instead of simply tap delay line measuring with the dual sampling, to also reduce the resolution. Thank you for your listening, and if you have any questions. And sorry, I was a little bit difficult to present like this.
Thank you, Arash.
Sure.
Okay, questions?
Oh, no, I could turn on my video.
So I have a question about this neural network. So as far as I understood, you're not, this is not implemented on the FPGA, or I did it get wrong?
I don't know. I heard my voice twice, so I don't know. Okay.
Sorry, my bad.
No, okay, it's okay. The first thing that we did is gathering data from the delay lines and the counter, then train a model with this data and also test the model. But then we try to use a TPU implemented on FPGA to do the same, and it works, but the speed was still very problematic. So this is what we are working on that. But the training the model is outside FPGA.
There is another question.
Very quick. Can you describe exactly, or in a quick way, what this neural network do? How can you calibrate the TDC with a neural network?
Okay. As you know, I can hear my voice again. Okay, as you know, the calibration of TDC is usually doing, it's common to do the test, code density test, which runs random signals for a long time to have all the possible combinations that can happen into the delay line and find the weight of the beans after that. But what we did, we just run long test on the delay on the whole TDC, like for these two channel, delay line 1, delay line 2, and the counter. And it, as I told you, each delay line has 464 delay elements, plus the counter was implemented on 12 bits. So we give the neural network all these combinations, like 2 multiplied by 464 plus 12, which 900 and something, I don't remember exactly. And we tried different layers, and also it works with just one 64 neuron layer. And we trained this model based on this input and also tested, and it reduced lots of the errors that we had before.
Okay, thanks, Arash. Let's move to the next presentation.